All right. So the goal for today, we want to do our whiteboard review for Stopper Lab, and I'll give you some details on that in a minute. You will not be drawing all your graphs. Okay, you'll just be talking about your results and interpreting them. And then we will use worksheet 3, possibly worksheet 4. We haven't gotten that far in my other classes yet, but we'll see. Just to review for the test, and they're not assignments. They've been out on the back table for a few days now. They're also on Axis, and the keys for both are also on Axis. And also there's an additional review sheet on Axis with an answer key. Highly recommend that as you prepare for the test. And then reminders, the test is next class, which is Friday. And then because of that, the lab report is pushed till Monday. Keep an eye on Axis though. I'm considering pushing it the lab report, not the test, pushing the lab report one more day because I think there's a bunch of big events going on this weekend. So I may give a little bit extra time in the lab report. So I'll probably do that, but I just realized all the things that are happening this weekend. And so, but I'll let you know Friday and I'll change it on Axis if I make that final decision. But, you know, keep working on it, try to make progress. And so that's it for overview and review for schedule. Any questions about that before we dive in? All right, anybody see Massimo today?
Yes.
Okay, hopefully he's on his way. Maybe his advisory group went a little long. All right, so let me tell you about the test first, and then we'll have you break up into your lab groups and start working on preparing for the whiteboard presentations. In terms of the test, and this is actually on Axis also, so if you click on the description of the test, exactly this information is there. So the top part just tells you the breakdown, 18 multiple choice questions for FRQ style. And in the 18 multiple choice, there are 2 of them that are multiple correct, and overall the total points are 20 points. So it's not that those 2 multiple correct are worth 20, but overall it's worth 20 points. So there's 16 with only 1 right answer with 1 point apiece. There's 2 that are multiple correct worth 2 points each. And then for the FRQs, they're worth 9 points, 4 points, 10 points, and 7 points accordingly in that order for a total of 30. So much like last time, it's a 50-point test. It'll be recorded as a percent out of 100 so that the curve's easier to manage, but it's a 50-point test. It is a 65-minute test, so it gauges 25 minutes estimated time for the multiple choice, and then 40 minutes for the FRQ portion. So that's how you should pace yourself. And I can remind you of that Friday as well, but just as you're thinking ahead. Now, I don't often give a lot of clues, but I'm actually giving a few this time because yeah, I think this unit's relatively tricky, and we've had a lot of people in and out with illness and stuff like that. So gonna give a few extra bonus thoughts here. These first 2 bullet points are specifically focused on the multiple choice. So I told you back right after Christmas when we were learning about electric force and comparing that to the gravitational force that equation is similar, and that I put 1 multiple choice question on electric force there. So make sure that you are reviewing electric force and are prepared to answer that multiple choice question. If you remember, we took 1 day, we did the notes, and then the next 3 class periods in a row, we did a practice problem at the beginning as warm up. So that's what you should be reviewing. You can't always go back and watch those videos, or at least the beginning of those videos if you want on YouTube, if you need a little refresher, or you can look back in your notes if you took good notes of that. But there is 1 in the multiple choice. Several of the questions in the multiple choice are proportional reasoning style questions. So like if the acceleration does this, what happens to the force? If the radius does this, what happens to the velocity? Those kinds of things where you're trying to proportionally think through as one item changes, what happens to the other. And so those are your 2 hints for the multiple choice. Obviously not a lot of information there, but a bit. And then I'm giving you a little bit more detail on the FRQs, and I usually don't tell you much at all about them, but again, giving you a little bonus here. The first one is a roller coaster problem, the 9-point question. And it's really just math driven, like using the equations correctly, making sure you can think through and solve problems mathematically. The second one is a ranking question, very much like the one we practiced on worksheet 3 last time, where you're looking at a scenario and then ranking the people or the objects by their acceleration or their force or whatever have you. And that one's just worth 4 points. It's a shorter question. And then the third one is the biggest 10-point question, vertical circle. And it is requiring you to draw some free body diagrams and then also deriving equations, meaning like, here's the information, use M for mass, use V for velocity, use A for acceleration, and derive an equation for that kind of a deal. So you're not actually given numbers, you're asked to basically solve it just using the variables. And then the last one is a gravitational force question. It's got a couple different parts because it's not all just that single formula. It's, can you apply it to forces? Can you apply it to centripetal force and centripetal motion? And so that is the last 7-point question. So that gives you a little bit more information than I typically provide, but like I said, with the number of students we've had in and out and missing class and such, I want to try to give you a bit more bonus. And I mentioned it a bit ago, but in case you fell asleep for a few seconds, that review on Axis, chef's kiss, great stuff. Make sure you check that out as you're preparing for this test.
Which one, number 5?
The review worksheet on Unit 3. Yeah. All right. Any questions?
Is that on Axis?
Yeah, if you click on the test in the assignments, it'll get in the description. All right. Okay, so you should be prepared and knowing what to think about. If I were studying for it, I know it's on it, so if I were prioritizing, I would say going over the worksheets that some we've covered in class and others I've just provided for review. The keys for all of them are on Axis. So even the ones we've done and the ones we won't have time to finish, they're all on there. So you can try those. I'd say that's probably your number one resource for this test in terms of review. Making sure you understand those questions, looking through the keys, and making sure you're, really clear on how those get solved. And then secondly, I would say probably go to AP Classroom and, watch the daily videos, maybe do a few topic questions, practice. That would be my second recommendation. Third would be to go through your textbook. I think it's chapter 6 in your textbook on centripetal motion. Just that would be third. And then fourth would be positive physics. I think positive physics is really good for certain things, but you would have to do a lot of practice to cover all the things you would need to in positive physics. So I don't think it's as time efficient. If you were just taking a week to prepare, that might be great. But since you just have a few days left, I wouldn't necessarily prioritize that. So that's what I would think of in terms of my suggestions. All right, so we've talked about the test. Let's get to the whiteboard review. So for the stopper lab, again, I'm not going to ask you to draw your graphs this time. Often we do that and we write out the mathematical formulas and look at the model, but we're not going to do that this time. Primarily just because I want to use as much time as we can today to keep reviewing and practicing problems for the test as well. So instead of drawing the graphs and the mathematical models, I just want you to focus on these 6 toagamers and tell me, what do you think the relationship is? And you might not have done this one, and it's okay. You might only have 5 if you chose not to do the optional or you just haven't had time yet. But I want your group to say, and you can just do them in this order, what is the relationship between tension force and tangential velocity? Is it linear? Quadratic? If it's quadratic, what did you have to square to make it linear? Okay, is it inverse? What is the relationship? And then for force and acceleration, again, same thing. What is it? Linear, quadratic, inverse? And then same thing for these, at least this one if you've had time, and then these 2. Okay, so 5 or 6 if you did have time to do the optional one. And so just quick brief statements on the whiteboard. This one, we think it's this. This one, we think it's this. This one, we think it's this. So I'm going to give you like 10 or 15 minutes to sort of get with your group, hash it out, make sure you have a good idea. And if we ask any questions that you don't have to show the graph, but just tell us what drew you to that conclusion. Or you could even do this, maybe your data tells you it's one thing, but logically, as you think through the different equations, you think, I don't know that it should be that. You could comment about that too during your presentation. All right? Any questions? All right, go ahead and get with your groups, get those whiteboards ready. We'll start in about 15 minutes. As each group presents, we're trying to see if there is a trend from group to group on these relationships. Do we see a trend in tension force and tangential velocity? Do we see a trend in tension force and acceleration? And then in the end, I'll tell you what they all are as we finalize it. So what I want you to do when you're finished and you're writing your conclusion is to say, well, our data says this, but when we stop and think about the actual physics behind it and the equations that guide it, it should be this. Therefore, here are some errors that may have led to, our wrong conclusion with the data. And we'll talk a little bit about the errors later today as well. All right, so whoever's, back there in that back row, let's get you guys going first. Just come on up here to the front and tell us what you came up with.
I think it's Luke's group.
Luke or Trevor, someone in that, whoever's, yeah, any of you back there.
Yeah.
I'm just trying. We'll go first. Why not?
All right.
Yeah, we'll go first.
All right.
We'll do it.
Why not?
Lead the way.
Why do you go?
We also have our.
So, wait, is this what you wanted us to test?
Yeah, the camera's right here, so just, yep, that's good.
All right, so this is what we did. We did this just with the equation, like with the few equations there is. So, tangential force or versus velocity. Is this tangential force?
Tension force.
Tension force versus velocity is quadratic because in the equation, Ft v squared.
And then tension force for centrifugal acceleration is linear. There's tension force and acceleration like that.
And then you want to go on?
Radius versus I think it's in velocity is quadratic, and there's the equation for that one.
And then radius versus centripetal acceleration is inverse because it's at the bottom. I'll do the last two.
And mass and centrifugal acceleration is inverse because we solved our equation like that. And then mass and velocity is inverse quadratic because this is how our equation is when it's solved.
All right, so we've got quadratic and then linear, and then we've got quadratic, and then,
Inverse,
inverse.
inverse quadratic.
and then inverse. Okay, all right, good. So let's, don't erase that in case we need to refer back to it. Let's have somebody else in that back row, Trevor or Luke, either one of you, your group, go ahead and come up.
Use yours.
So we got same thing using the equation. The force versus velocity is quadratic squared, so we have to linearize it. And the force versus acceleration is linear. Yeah, you can see that there. And we can do this here.
So radius versus velocity is quadratic because that, if you take r to the other side of the equation, r equals v squared, so quadratic. And we didn't calculate for the centrifugal acceleration yet, but we assume that it's going to be inverse because r is on the bottom.
And for the mass versus velocity, you got no correlation because there is no mass in this. And same thing for the mass times acceleration.
All right. And any questions for this group? I forgot to ask for the first group. We've got similarities, so we got quadratic, linear, quadratic, and then no correlation. So they had some ideas about correlation for mass, but you're saying no correlation. All right, let's go Luke's group.
So for all of these, we looked at the equations as well as the data. We wrote out what the correlations were with each other and the equations. So for tension force and tangential velocity, we got their quadratic, but directly proportional.
Sure, so for the radius and tangential velocity, we said that radius is directly proportional since it's in the same.
I'll just keep going.
Tension force versus centripetal acceleration. We saw that the greater the tension force, the greater the centripetal acceleration, so that means they're directly proportional. And the centripetal acceleration increases quadratically. And we got that from the equation and our data.
And for both when you change the stopper masses, for like this the acceleration and for the velocity, when the stopper mass increases in both, then it results in either the velocity or the acceleration decreasing from the data that Mr. Webb posted.
All right. Any questions for this group? So we've got some consistency, a few variations, but we're seeing, some linear quadratic relationships and no correlation. Some, like I said, some consistency with inverse too, but we're not getting like that 100% across the board, right? We're getting a lot of variety. So, all right, let's keep going. Let's go to, I think everybody in the back row is gone. Jake, your group gone yet?
No.
Nope, so let's have you guys go.
Okay, so we just kind of put all of our calculations on our calculator onto the board and what we got for our graph. For the mass of stopper and the tangential velocity, we got inverse, and then for mass of stopper and acceleration, we also got inverse.
And then over here, we have, tension force and tangential velocity being
And then
linear, and then, tension force and acceleration also being linear. And then, at the bottom, we have, on the bottom right, we have radius and tangential velocity being, inverse quadratic.
yeah, it's quadratic. We just put the wrong radius should be on the y and velocity should be on the x, and it'd be a normal exponential graph.
And then we have linear x in the bottom left.
All right, and the way you did it there was showing that kind of square root shape. There's nothing wrong with having it that way. If you flipped it, like Jake said, you'd see the quadratic curve, which is more familiar. But you can correct that still by squaring the velocity, and that'll still correct that change. So there's not a problem with drawing it that way at all. So, questions for this group? All right, and then Tim, I think your group needs to go, right? I think that may be the last group. I'm looking up the front rows, looks like everybody's gone now.
Okay, so for tangential force and tangential velocity, we got the quadratic because this is the tangential force formula. Wait, yeah, and this velocity. So we see that both there's velocity in both the sides, and one side is squared, it's quadratic.
And then, tension force and centripetal acceleration, we said it was linear, pretty much the same principle, and radius and centripetal acceleration, we said was inverse, but we're not 100% sure on that one.
Well, did you say about this or about that? So radius and tangential velocity here is, we see that radius in numerator, and on the right side it's in denominator, so it's like inverse proportional. And here, stopper mass tangential velocity again, it's linear because it's in numerator and it's like in power of 1 on both sides. And the last one is stopper mass centripetal velocity. Centripetal acceleration is, there's no correlation because there's no mass force in centripetal acceleration.
All right, good. Any questions for this group? All right, nicely done for all the groups. So let's talk through. It's interesting because this class took a much more mathematical approach. Maybe I leaned too heavy on that when I was giving you suggestions. Other groups were much more data-driven in their analysis in prior classes. So just interesting observation for me to see that. I think it's important to do kind of a combination of both. Now, it is true that it's hard to get good data in this experiment. So if you're only data-driven, you're probably going to come up with some wrong conclusions. If you're only math-driven, though, this one actually has a couple little twists to it that I saw caught a few of you, and that's okay. It's like part of the learning process. And we're going to try to iron all that out today and so what I want you to be thinking about now is, okay, you have your ideas based on either your data and or your mathematical evaluation. We're going to try to layer both of that. I don't have data to really show you, but I have some from last year that I'll show you a couple. And then I'll also talk about the math, but I'll also talk about the concepts because you sort of have to marry all three things together to draw the correct conclusions on this one. So what I would encourage you to do is maybe keep a few notes as we go through, whether it's on your rubric or just in your journal or wherever, of what the relationship should be. So when you're writing your conclusion, you can say, well, this one, our data looks like it should be this, but in reality, we think it should be this. So here are some errors that probably resulted in an improper set of data. All right, so that's what I would recommend as we go through. First up, tension force and tangential velocity. If my memory is correct here, thinking through, we had a mix of linear and quadratic. I think everyone either had one or the other. And if we think about the scenario, the tension force is going to change the acceleration, right? Because forces cause acceleration. Right? And if the acceleration changes, then we should see something happening with the velocity and the radius, depending on what we're manipulating and what we're holding constant. If we think about the equation with this experiment, let's go back to this slide here. This equation of F equals mv squared over r, when we relate those things together that way, the force should be quadratically proportional to the velocity. Okay, so as the force is changing, the acceleration should change. And since velocity is part of that acceleration component, we can see that it's quadratic, or it should be quadratic. So the shape of that first graph, this one, it should be something like this. If you put force on the y and velocity on the x. Now, if you put it the other way around, it's going to look more like a square root. But if you put it force on the y and velocity on the x, you should see that traditional sort of quadratic. Now, this is something about linearization that I've noticed in most of the classes. There's still some students, because we haven't done it in a while, and I think it was just hazy enough that some students were doing it wrong. So this is what I heard some groups saying, well, oh, this looks quadratic. So that's like a y equals mx squared, right? That's the pattern. And so students were saying, if it's got that shape, the x is squared. So if I want to linearize it, I need to square root the x. But that's not the proper train of thought for linearization. What we're saying is this is just force versus velocity and nothing's squared, right? Because nothing's squared, it looks curved. And so I know when it has that curved relationship, it should be the x squared. And so if I square the x, that should fix it. Okay, so you don't try to undo this. This tells you what you need to do to fix the original. All right, so if this are two first power variables and it isn't straight, then the shape tells me quadratic, so I square the x, that should make it straight. Okay, so you use that sort of parent formula to tell you what to do. You don't try to undo the parent formula, that's giving you your clue. All right, so parent formula for this, oh, that's the y equals x squared, so if we square the x, that should fix it. So that's how you think through linearization. All right, another way to process it, the force is increasing faster than the velocity in this curve, right? So I need to help the velocity catch up. So I'm going to square the velocity, and that'll pull that back down and make it straight instead of curved. It'll help the velocity increase faster by squaring it, and then it'll be able to keep up with the force. So you can kind of think it through a few ways, but in my mind, I always just think, well, that's the parent equation, so the parent equation tells me what I need to do to fix it and make it linear. All right, now tension, force, and acceleration. Well, we don't really have it on this screen written, but this really is just F equals MA, right? It's just that the A is centripetal. It doesn't look like a C. We agree with that? If this is a centripetal force, then we're just saying that's the same as M times centripetal acceleration. So if I'm looking at this and this, what should their relationship be? Linear, should be directly proportional. So that one should already be a straight line. You shouldn't have to do any correcting to that one. Now, so I don't forget to say it later, when you're analyzing your graphs in your report, don't worry about intercept, slope, and area under the curve for the non-linear. Okay, only worry about that for the linear graphs. So for the first one, it's not linear, so you have to linearize it. And then you analyze the slope, intercept, and area under the curve for the linearized form, not the curved form. For this one, it's already linear, so you don't have to do anything to it. You can just analyze it directly. Okay? Any questions about the first two?
And you just said you don't have to analyze the curved form, correct?
You do not have to analyze the curved form of the graph, just the linear ones. So either the linearized version of the curved one, or if it was already linear, just that one. Yep. We okay with number one, those two items?
Yep.
All right. Now we get into a little bit hairier territory. I like the way Josh said this for number two, the first one, radius and tangential velocity. He was pointing, and I'll do it on the screen so those watching the video can see it maybe better than over there on the board, but he was pointing to this equation over here, a equals v squared over r, and said, well, if I just solve it for r would equal 1 over a times v squared, right? If I just multiply both sides by r and then divide both sides by a, that's what it would be if I were solving it for r. So what does it look like if I'm graphing r versus v? Looks quadratic. Now for all of these things, we need to be asking ourselves one other question, because your data may or may not reflect this. So think about the equation, but then also think about which way did you graph it. All right, so if you put the r on the y, then it's going to look like that traditional quadratic curve, right? And you should square the v. If you put the v, the velocity, on the y-axis, it's going to look like a square root. So you still have to square the v to correct it, okay? So it's going to give you the same relationship either way, but the graph looks different. If you put r on the y-axis, it's going to look like a traditional right side of a smiling parabola, right? If you put v in the y-axis and r on the x, it's going to look like a sideways parabola, the top half of a sideways parabola, square root, okay? So they're both quadratic, it's just how you graph it. And then the third thing is, we should also be asking ourselves, conceptually, does it make sense? So conceptually, if I change the radius, should it affect the velocity? Yeah, we can see that. It won't take too long to do this because I want to make sure we have a chance to review for the test, but if I keep the stopper mass constant, because I'm not changing it, and I keep this constant, right now I've got kind of a large radius, right? Too large. All right, there we go. That's large enough. So I've got a large radius. If I make the radius smaller, does it change the velocity?
Yes.
Yeah. So there is a relationship between the velocity and the radius, right? As I change the radius, the velocity changes. Did that change the force at all?
No.
No, because the force is caused by this, and I never changed that, right? So you do have to think through conceptually too, does it make sense? All right. Back to this one. Now here's where it gets a little bit hairy. Radius and centripetal acceleration. If you just look at the equation, what does it look like? Inverse. But does the radius change the acceleration? Does radius cause acceleration? What causes acceleration? Force. And that I just demonstrated. Did I change the force?
No.
No. So would changing the radius change the force? No. If it doesn't change the force, can it cause the acceleration to change? What causes changes in velocity? Or what causes acceleration? Force. If the radius doesn't change the force, can it change the acceleration?
No.
No, because only forces cause acceleration. So if the radius can't change the force, the radius can't change the acceleration. So this is one where if you just look at the equation, you think, oh, I bet that's going to be inverse. But you have to stop and think about what causes what. Forces cause acceleration, right? The radius doesn't cause acceleration. The radius changes the velocity. Because I kept the force constant. So what if the force is constant, what has to be true about the acceleration? It was also constant. So if I change the radius, it doesn't change this, it changes that. Okay? So the radius and the velocity are connected. As I change the radius, the velocity changes. It doesn't change acceleration because I didn't change the force at all.
Quadratic, right?
So for radius and centripetal acceleration, it should have no correlation.
But for the first one.
Yeah, this one should be quadratic because the velocity should be squared.
Isn't acceleration just changing velocity?
Acceleration is a change in velocity, but in centripetal motion, it's not the speed that's changing, it's just the direction.
Oh.
So the speed, we're trying to keep the speed constant. That will be a source of error though, because if any of you ever did do the spinning part, you know that it's literally impossible to keep it constant the whole time. You're constantly putting force into it, so it's going to be speeding up and slowing down even within one cycle, let alone multiple cycles. So it's impossible to keep it perfectly even on velocity when we're doing it the way we did it. So that would be a source of error because the speed wasn't constant, even though we were trying to make it so. All right, so we get on number 2, quadratic for the first one, we should square the velocity. And then for the second one, there actually is no correlation because the radius doesn't change the acceleration. The radius only changes the velocity. The force has to change for the acceleration to change. All right. Number 3, stopper mass and tangential velocity. So according to the equation, how does stopper mass affect the tangential velocity? It doesn't. Stopper mass and centripetal acceleration. If this is the equation for centripetal acceleration, how does mass affect the centripetal acceleration? It doesn't. So for those last two, it should be no correlation. If you just look at this, you might start thinking, oh, maybe it's inverse or some other kind of relationship, but if I think about this, what's actually creating the tension in the string?
The way at the bottom.
Just this. So changing the stopper is going to maybe cause a different radius to velocity ratio, but it's not going to change the force. Therefore, it's not going to change the acceleration. This is still the core force. So a bigger stopper just changes my ratio to radius and velocity. It doesn't change the acceleration, doesn't change the tension force. It's actually being created by this. All right. All right. Any questions? So if your graphs don't reflect those things, fine. Just say in your conclusion, our graph looks like it's inverse, but should have been linear. Or our graph looks like inverse, but should have been no correlation. Or our graph looks linear, but should have been quadratic. And then, so some sources of error, like you could summarize this at the end, like give me a little bit about each one, and then say, you could even say, so there were some sources of error that made our data faulty, see below. And at the bottom, you can say, some sources of error in this experiment that contributed to the improper data include. Well, we said one a minute ago with Sunny's comment that velocity shouldn't be changing according to the design of this experiment, but in actuality, we know it is. It's impossible to keep it perfectly constant. So that would be like an error. The velocity wasn't truly constant, the speed. What are some other errors that you know of?
The angle, like, it was going too slow, so it started to get affected by gravity.
Yeah, so that angle of the stopper, it needs to be parallel to the ground. Otherwise, we're thinking really about that component, and we need to use trig, and we didn't even measure the angle or anything. So the more that stopper sags, the more error. Yeah, Luke?
Maybe like the not the paperclip, but whatever we had on the string, maybe that caused friction with the bottom of the holder.
Yeah, if you use the clip or even just tape, that is going to create some friction between the tape or the clip and the tube, right? Which is adding another force in. Yeah, Owen?
Maybe the string stretching?
Possibly, yeah, there could be a little bit of string stretch, especially as you get a really heavy tension force weight on the other and a bigger stopper on the other, and that could create a little bit more stretch to the string, so the radius wouldn't be constant.
Not getting like the timing right, like once you're recorded.
Yeah, especially if you're using stopwatch technique, human reaction time is going to be a big factor. And even if you're using video, because the speed isn't constant, you might have analyzed a video clip where it was going slower than it should have been, or it was going faster than it should have been. So there's always going to be, that kind of goes back to the first one we mentioned with the velocity not really being constant. But there's one other place where there should be some friction as well, and you can actually hear it when you're doing it. Yeah, Ruby?
The string at the top of the tube.
Yeah, the string at the top of the tube, it's rubbing the whole time, right? And especially, as Massimo mentioned, if that stopper's angling down, that creates even more contact, which is gonna potentially create more friction. So, because there's a greater normal force, the more that angle is, the greater the downward normal force on that tube. So greater friction. All right, so all of those things could be discussed and included in your evaluation of why your graphs maybe didn't turn out like we would expect them to. So any questions as we wrap this up today?
I've got one a little bit more specific to the situation.
Okay.
So on the simulation,
Uh-huh.
part of it was keeping the velocity constant instead of the tension force.
Right.
So for the second one, for example, I'm comparing radius to tangential velocity. Obviously, it's gonna look like that
Yeah.
it's the same, right? But I know that the period's changing. So should I just do some math to like get see this that the period's the same, and then what would happen to the velocity if the periods were the same?
I think what I would suggest for that, because you're limited in what you can do in the sim, I would say you should be able to do this one.
Yeah.
Which I made optional for them. And so I'll just make this one optional for you.
Okay.
So if you just do this one for the sim, you should be able to evaluate that without a lot of monkeying around.
Yeah, and then 3 is pretty easy.
And then
to see.
if you want to try to do this as an optional, you can, but it won't be required. We'll just flip flop that for you because the sim is set up different.
Yeah.
Yeah.
And I'll see what to do about it. I mean,
Yeah.
for
If you
3,
can come
I
up
might,
with,
for 3, I might just say the period's the same for it. So
Okay.
like, yeah, there's nothing.
because you actually could change the stopper mass on your.
But again, it reflects
In the
as the
velocity.
same velocity. Yeah. So.
Yeah, that's true. Yeah, so that first one and that third group would be kind of awkward.
Yeah. So I'll
Yeah.
You know.
All right. Any other questions? All right, so we'll put that to rest for now. Let's do a little review for the test. We've got about almost 20 minutes. Yeah, almost 20 minutes. That's not enough time for me to have you guys put the answers on the whiteboards though, so go ahead and put the whiteboards away, and then we'll look at some of these questions together just for a group review. Yeah, Ruby?
Could I go fill up my water bottle?
Yes, you may.
Thank you.
Man, I thought I was gonna make it through a whole year without hitting myself in the head with it.
That was a direct shot.
I like
It's a
stock.
glancing blow.
As soon as it
I can
hit
hear
the
it
wall, I
pretty
was
well.
like, it's about to hit your head.
Yeah. I knew I was in trouble when it started hitting things around me. That's yeah, I thought, man, I'm gonna have a year where I don't actually hit myself in the head. Not too good to be true.
Gosh, you went out of your way though. You seeked it out. Because you were done.
I mean, I probably demonstrated that thing 40 times.
Was that
in
the
all
first time
classes.
you hit yourself?
This year.
So we gotta see the only one.
Yeah. I mean, I have one more class, so you ain't over yet.
Let us know. Let us know how that goes.
But the good thing is this one was caught on video. So.
Yeah.
Oh yeah, you were.
So now there's gonna be little like clips showing up.
I'm gonna check the video.
I'll become a meme.
Sports Center top 10 Oaks
Physics, Oaks Christian physics.
They should put it in the Oaks News.
ESPN
Oaks News. All right, not top 10. That's hilarious. Okay, so let's get into this. I want to make sure we cover at least a couple of these questions. We won't necessarily be able to go through all of them, but I want to have some conversation about it and make sure you at least start to get some practice thinking them through. I told you already, one of the questions on the test is a roller coaster question. I'll say it's not exactly this format, but it is about roller coaster. So a lot of logic you're using here is going to carry over. Okay. So in this scenario, it's saying that roller coasters actually, when they have a loop, they don't make it so that the two curves are equal. They make this curve as you're going into the loop much broader in radius than the loop itself. And mathematically, they're just wanting you to see in this problem why. Okay, so that's the goal of their question. So they say we've got a roller coaster that's got 1,000 kilogram mass and it's moving at 22 meters per second when it reaches the bottom of that curve, which is a 10-meter radius. And then it's only going 8 meters per second when it gets to the top of the loop, which has a 5-meter radius. Which makes sense. It would be slowing down as it goes up, right? But it's still moving. 8 meters per second, that's a good sign, you know, that it's still moving. Now, the question says, okay, let's create some quantitative force diagrams to determine the size of the force on the rider by the seat at the top and the bottom. So what do we call that force of the seat on the rider? Normal force. All right. Which way is the normal force pointing at the bottom of that curve? Up. Which way is it pointing at the top of the loop? Down. Okay, so we got to think about that with our free body diagrams. For now, look at these free body diagrams, but don't worry about the numbers yet. All right? We'll talk about the numbers little by little, but just focus on the way things are pointing. All right, so obviously the weight's going to be down no matter what, but in this case, the normal force is down. In this case, the normal force is up. All right, second thing, when you're going down through that bottom curve, are you going to feel heavier or lighter at the bottom? Heavier. So that means the normal force is greater. It's upward and greater, right? Now, when you're going on the loop, do you feel heavier or lighter against the seat? Lighter. So the normal force will be less and down. All right. So where do they get these numbers in the free body diagram? Well, Fg is just the weight of the object. So they have chosen to use 10 instead of 9.8. And you always have the freedom to do that on my test, and you also always have the freedom to do that on College Board. I usually use 9.8 just out of habit, but if you use 10, it's perfectly acceptable by College Board, so it's perfectly acceptable for me too. So in that first row, all they're doing is finding the weight. 1,000 kilograms times acceleration due to gravity. They've just used 10 instead of 9.8. And again, you'll notice that they like to use that newtons per kilogram unit instead of meters per second squared. Means the same thing. Like my grandkids call me grandpa, my wife calls me husband. You guys call me Mr. Webb, but I'm still the same person all the time. It's just 9.8 all the time. Just the units change depending on what the situation is. If it's newtons per kilogram, it's usually a gravitational field. If it's meters per second, it's gravitational acceleration, but it really is the same thing either way. Yeah. And then the second row we see, and this is, if you don't catch anything else today, I hope you catch this, because this helps you solve almost all these circular motion problems. The net force for circular motion is always centripetal force. Okay? The net force is always centripetal force. If it wasn't, the object wouldn't go in a circle. It would keep going straight. Okay? The net force is always the centripetal force. Not necessarily the normal force, the net force though. It could be the normal force in certain problems, but it will always be the net force. Okay? So here they're just saying, well, there's two ways to calculate the net force. One is, we know it's centripetal, so mv squared over r. That's just how we calculate centripetal force. The second way is normal minus weight, because the normal force is up, the weight force is down, so we know we should subtract them. And the normal force is bigger, because if I draw the kissing circle here, where's the center of the circle? Above or below the track?
Above.
Above, so the force is up, right? The net force is up. So the normal has to be larger than the weight. So two ways to find net force. It's centripetal, mv squared over r, and we've got two forces competing, so normal minus weight. And then they've just plugged in the numbers. 1,000 kilograms is the mass, that was given. 22 meters per second, and then they square it, was given. 10-meter radius was given, they just plug it all in. And the centripetal force is approximately 48,000. Now I believe they've just rounded it off here for sig figs perhaps, because this only has two. I'm not sure. It went, somehow it goes to from 48,400 just to 48,000 when they subtract them, but I think they were just trying to do some kind of sig fig, or maybe they made a mistake. But in the end, we find the net force and we plug it in here. We found the weight, we plug it in here, and we solve for the normal force. Okay, find the net force here, plug it in. Find the weight force here, plug it in, solve for the normal force. Now, once we put it on the free body diagram, we can see, oh yeah, it makes sense. The normal force is 58,000 newtons up, weight force is 10,000 down, so the net force is 48,000, and the net force is the centripetal force. Okay, so you can kind of full circle it, as long as you keep that in mind. The net force is the centripetal force. Okay, if you keep that in mind, that will help you solve almost every problem. So the weight of the cart, 1,000 kilograms, 10,000 newtons, feels like 58,000 newtons. So that track needs to be able to support 58,000 newtons. How much would the track have to support if the cart was just sitting there?
Just
Just the
10,000.
10,000. But it isn't just holding it, right? It's holding it and pushing it back to the center. And because of the speed of the cart and the radius of the curve, it has to push back with 48,000. So the total is 58,000, right? In terms of the normal force. It's got to cover the centripetal to push it back, and it's also got to bear the weight. All right, now the second scenario, if the normal force and the weight force are both down, what do we do with those?
Adam.
We add them. They're both pointing the same direction. And so, but is it still a circular path?
Mhm.
Yeah, it's a curved path, so it's still centripetal. So they're doing the same basic idea here. The net force is centripetal, and the net force is these two things added together because they're both pointed down. And then they just solve for centripetal, plug it in for the net force. They know the weight is still 10,000. They plug that in for FG, and they solve for normal. So at the top of the loop, the seat's only pushing with 2,800, which is what we thought. Should be very light, right? Not pushing very hard at all. So engineering-wise, does the top of the loop has to have as much support as the bottom of that curve?
It has to have more, no?
Which one has to bear more force?
The top?
The top's 2,800.
Oh, the bottom.
Yeah, the bottom's 58,000, right? So that bottom has to bear the weight of the cart and redirect the cart. At the top of the loop, does it have to bear the weight? No, because its inertia is going up, right? So it doesn't really have to bear the weight. It's just going to have to bear that little bit of force to push it back to the center. So the top doesn't have to be as structurally sound. Now it still has to be, obviously, but in terms of which one has to bear the most force, it's the bottom, not the top. Now part B says, well, what if they got mixed up and they decided to make the bottom curve only a 5-meter radius and the loop a 10-meter radius? They did it backwards. Why is that a problem? Well, do the free body diagrams change in that situation? Not the
No.
numbers, but just the diagram itself. No, still the same diagrams. Does the math change in terms of the setup? The setup doesn't.
Oh, the formulas?
Formulas and stuff? No, it's all the same. The numbers change, right? And what's the only number that changes?
Radius.
The radius. So we just do the same exact thing, but we change 10 to 5 and 5 to 10. We're just flipping the radius, right? If you do that, you find out that now that bottom curve has to bear 107,000 newtons because that tighter curve. It's got to bear the weight and then push it harder to make that go that tighter curve. So now the bottom of that track has to be way stronger, nearly double, right? Almost twice as strong to bear it. And then we got a problem at the top of the loop because our calculations say that the normal force should be the other direction. The normal force should be pushing us back to the center, and it's saying actually it would be like holding on to you, which a seat can't do, right? So that's why they got seat belts and stuff. If they had it designed this way, the normal force, according to this -3, if we said everything else was down, right? If we get a negative number, it must be the opposite direction. But the seat can't push you that way because it's above you, right? So we got a problem. You're falling out of your seat. You better hope there's straps or something holding you in. Or maybe the roller coaster doesn't even make it through the loop. Like it just gets and it comes back down. That's not a good ride. Well, maybe it could be, but yeah. Either way, they've got a design problem here.
Wait, so. Okay,
Yeah, but that's like, no, there's.
So when you're making a roller coaster as an engineer, you want to make it fun. But you also got to make sure that it's structurally logical, that it doesn't have to bear so much force that you can't structurally provide it. And also you got to make sure that the riders don't fall out, and that's a problem. All right, so hopefully this key is on Access 2. You can look at it again if you want to. I don't want to spend too much time because really the math here on part B is identical in setup. All the equations are the same. It's just changing the radius, and it really makes a big difference. Because I want to have a chance to talk about Tarzan here. All right, so don't worry too much about part A. I think the wording of the question's a little bit funny, but what I really want you to get from part A is if Tarzan is swinging on this vine, he's got a long radius, the vine has a long stretch, right, a long length. And so he's gonna have a certain centripetal motion here, and then the vine gets caught on a branch, and then the radius that is swinging is only 2 meters. So if the radius gets smaller, what happens to the acceleration?
It's bigger.
That gets bigger. If the acceleration gets bigger, what happens to the force?
Bigger.
It gets bigger. Okay, so the grip Tarzan has to have, he has to be able to, like if he was just hanging, how much weight would he have to bear?
Is the weight?
Just his weight, right? That's the only force. But when he's swinging, he has to grip strong enough to hold his own weight and strong enough to bear that centripetal force, pushing him back into a circle, or pulling him back into a circle, right? So the force is going to get a lot greater here when the radius decreases to 2 meters. And that's what this problem is asking you to think of. Now, if Tarzan can't hang on,
That's still a lot though.
yeah, it is a lot. If Tarzan can't hang on, he becomes a projectile. And so right here, he just takes off tangent to the circle, but then he's no longer hanging on to anything, so gravity takes over and he just follows the parabolic path like any other projectile.
Part A, is he not standing on the branch?
Well, they're talking about part A is when he like
Like
jumps. Like I said, the wording for part A is a little awkward. That's why I just wanted to talk through what's happening. I'm more concerned about understanding this, because this is a question I've seen before. Draw the path. If the string broke here, or the vine broke here, or the friction gave up here, draw the path. And so know that it starts tangent, but then if gravity takes over, it's just a projectile path.
Would they ever ask us a question where it's like from point A and he falls off at point C? How far is he going to land from point A?
They could. So if you found the centripetal velocity, that would be VO. Right?
That's true. That's crazy.
Oh, that's disgusting.
Yeah.
And
That's a lot of work.
if it happens to be, because I've only seen it this way, it happens to be where that VO is horizontal,
Okay.
that makes it easier. If it's at an angle, then you gotta take trig, they can do it, but.
I feel like I get handled.
That would be terrible.
Yeah.
That should be the only question.
All right, let's look at the math here. So we've got this tension in the vine that's holding Tarzan up, and we've got Tarzan's weight going down. And is the net force centripetal?
Yeah.
Yeah, because Tarzan's going along a curve, right? So it is centripetal. But the net force is also the difference between these, right? Because one's up and one's down, so the difference between them would be the net force. And if we think about his path, if he's swinging this way, where's the kissing circle? Above or below him? Above. So the net force goes up, meaning the tension has to be greater than the weight, right? So that's another way to think through, which way do I subtract it? Look at the kissing circle. Where's the kissing circle at? Is it above or below? If it's above, the upward force has to be larger. All right, so they're setting it up a little bit different, but with the same logic. The net force is tension minus weight, but also it is mv squared over r because it's centripetal. And then they just solve it for Ft by adding Fg to both sides. So the tension would be the centripetal force plus his weight, which if you think about it, Tarzan has to hang on for his weight, and he has to hang on for the centripetal force. He's got, because it's pulling him back to the center, right? He's got to be able to grip that too. So if we plug that in, his mass times his velocity over the radius, that's the centripetal force. He's got to bear that much, which is about 490 newtons. So like 49 kilograms or 100 and some pounds of force due to centripetal. And then his own weight, the 800 newtons, the 80 kilograms, 170 or so pounds. So like 280 pounds or whatever he's got to be able to hang on to. Got to be kind of strong, right? Now, if we look at the next one though, where it changes to 2, his weight doesn't change, right? It's still just 800. But because of that radius being smaller, now the centripetal force is almost 2,000 instead of only 490. So now he has to bear 2,800 newtons or 280 kilograms or like 600 pounds of force. Okay, so he's going to be pretty strong. It's like 3 times his weight. And so he's going to have to be really strong. Probably he won't be able to hang on to 600 plus pounds of force, and he's going to become that projectile, right? Or the vine breaks. All right, questions? All right, if you have questions on anything as you're preparing for the test on Friday, you can stick around now and ask them. You can come on in later, after school today, lunch tomorrow. Bring those questions. I can try to help you work through some things. All these keys are on Access, so you can use them as you review. Don't forget that review worksheet on Access. Unit 3.